Hello, this is our third segment on sedimentary rocks, about the formation of sedimentary rocks, and this time we're focusing on clastic sediment formation and transport. So by the end of this, and by the end of your work in this topic, you are expected to be able to explain how clastic sediments form, identify how clastic sediments are classified, match the size ranges of clastic sediment sizes with the name of each particle size, identify major things that transport sediments, explain how transport energy relates to the size of clastic sediments that are moved, describe what conditions lead to sediment deposition, describe the major changes in sediments when they initially form to when they have been transported a large distance. Compare and contrast the size of class that can be transported by fast water, slowly moving water, wind, and glacier ice. And finally, compare and contrast deposits of high energy streams, low energy streams, beaches, deep ocean and lake, and wind and ice. Our first big idea to understand about sediments is that sediments are categorized by how they formed. And so from working through the other videos on weathering, you likely know that we've got two different processes or sets of processes that can create sediments. So the first one is physical weathering. Physical weathering creates solid sediments. These are also known as clasts. And we've got an example here of physical weathering in granite. Chemical weathering creates mostly dissolved or chemical sediments, but it turns out some chemical weathering results in clasts as well. So we've got two examples. One is that chemical weathering can produce dissolved sediments like halite, dissolving in water here, and creating dissolved ions of sodium and chlorine. And again, we call these dissolved or chemical sediments when they're completely surrounded by water molecules and no longer in their original configuration or bonding. As we also learned, there are some ways we can get solids, not dissolved sediments, from the weathering of certain minerals such as potassium feldspar or other feldspars by chemical alteration. So again, our example of kaolinite. So the big message here is physical weathering always makes clasts. Chemical weathering mostly makes dissolved sediments, but also some clasts. That is, the clay minerals are often our clay-sized particles. Clasts or solid sediments or clastic sediments are categorized by their size. So we've got in your textbook, I've kind of mocked it up here, the same basic information and images. We've got large sediment size to the left and small sediment size to the right. So we're actually going to start with the large sediment size. Gravel is the name that geologists use for clastic sediment or clasts that are made up of anything that is bigger than about 2 millimeters in diameter. So like across the thing, if we can, the sediment, a clast, if we think about it sort of like a sphere, even though we know it's not exactly a sphere. So it turns out 2 millimeters in diameter is about the thickness of a quarter. So you might think that's really small for gravel. Gravel is kind of a funny scientific term. There's no upper limit to it, so it can be huge. And we would still technically geologically call it gravel, like a car or house size piece of granite or something else. Most gravel's smaller. And so yes, anything bigger than 2 millimeters, about the thickness of a quarter, up on to the size of a car or a house, geologists call that gravel. There are some divisions that we sometimes make in what gravel is, like pebble, cobble, boulder, but those are all gravel. The slightly smaller, that is less than 2 millimeters, and also bigger than about the width of a human hair, or 0.06 millimeters, is sand. That is technically sand. And I think most of us have an idea of what sand is, and our sort of everyday definition is basically the same as the geologic definition. Usually it's sort of practically anything that feels gritty. So obviously, not obviously maybe, but we might in everyday life think of something that's bigger than 2 millimeters as sand, but technically that usually moves a little differently, and geologists consider that to be enough of a difference to be considered gravel. Mud is the name for any clastic sediment that's smaller than sand. And so this gets into like the size of a human hair, the thickness of a human hair, smaller than 0.06 millimeters. Mud is technically this grouping of two things that are often split into different sizes, silt and clay. Silt is smaller than sand, but basically bigger than clay, and silt is usually feeling a little bit gritty, kind of more like sand in some ways. Clay is smaller than the size of 0.002 millimeters. Aren't you glad you don't have to memorize this? And usually feels smooth. And we're talking about gritty and smooth, basically between your fingers. If you were to rub little particles of this, you would feel grittiness with silt, and it would feel smooth, like modeling clay with clay, because that's usually what it is. Similar composition. So technically any material can make mud or clay, but a lot of it is actually clay minerals. So that goes for everything that's in the mud category. So gravel is the best name for the largest size class, sand is intermediate, and mud is the smallest class. We've already discussed a little bit about getting a hard, solid sedimentary rock usually requires weathering, erosion and transport, deposition and lithification. And this part of our discussion, this video lecture, covers primarily erosion and transport and deposition. So when we've gotten introduced now to the three main sizes of particles, of clastic particles or clastic sediment, in order to understand what's going on with erosion and transport and deposition, what we've learned by examining modern sediments and modern processes and modern things that move sediments is that there's three things that vary, that are different in different situations about the sediment. And so those three things are the size of the sediment, which we've already discussed, gravel to clay, the rounding or the shape of the sediment grains or particles themselves. And they can be angular, like lots of pointy, just broken edges, to quite well-rounded, smoother. And they can be deposited in a collection that's either a really broad range of grain sizes, or it can be something where it's basically just one size, like maybe just sand. And so that's called sorting. And so we're going to work on next what is meant by rounding or grain shape and sorting. And we're going to keep in mind what size could have to do with anything else as well. Geologists examine these three characteristics, as we just described, of clastic sediment to figure out how the sediment was eroded and transported. And this again is the size, the shape, and the sorting. So when we're talking about sediment size, we're talking about gravel, sand, or mud. And we've got kind of a new image here to help you understand what these characteristics sizes look like. When we're talking about sediment shape, here's a visual for that angular definition or angular type of sediment. Looks just broken, maybe like a just fractured or just cleaved mineral. And then more rounded things, more rounded particles that you're maybe more used to seeing at a beach in Michigan. Poor sorting or poorly sorted sediment will have all different grain sizes or a big range of grain size. It doesn't matter what the angularity is or the size, it's just going to be all different sizes. And the same thing goes for well sorted. That is, it doesn't matter what the angularity is, doesn't matter what the size is, but for well sorted sediments, this is going to be a very narrow range of sizes. So again, maybe it's just gravel or just sand or just silt. In any of those cases, we would say it's well sorted. First, all clastic sediments start out as poorly sorted, so representing all the grain sizes, and angular with sharp edges. This because most of the time they've been physically weathered, and physical weathering produces the size range of basically all sizes and the angular shape. Different processes or agents can move sediments or transport them, and at a fundamental level, the transportation energy of the agent or the process determines the size of the class that can be moved. High energy environments, such as a landslide due to gravity, a steep and fast mountain stream, and the flowing ice of a glacier, can move both huge and tiny particles, which geologists would classify as both gravel and all the way down to clay. Environments are agents of transport that can only move sand, such as waves on a beach or the wind, are considered to have moderate transport energy. Low transport energy environments, such as this flatter, slower stream, can move only mud. Moving water, as in streams and lakes or the ocean, varies greatly in the amount of transportation energy it has. Steep streams are high energy environments, so like our example on the last page, can move everything. Gently sloping streams, like the creeks and rivers near us, usually are moderate to low energy environments and can only transport and deposit sand to mud-sized sediment. At a beach, sand tends to be concentrated as the mud is carried off into a lake or to the ocean. Farther from shore in a lake or the ocean, water is almost perfectly still, especially towards the bottom, and only the smallest mud-sized sediments can be transported and deposited. This is a low-energy transport environment. Wind generally has a moderate transportation energy and can't move gravel, but can move sand and mud, so the gravel gets left behind. Wind can just move sand, usually, so dune deposits are almost exclusively sand. Mud-sized sediments can be carried long distances by wind and are carried away from dune settings. Glaciers, which are flowing ice, can carry all sediment sizes and deposit them then when the ice melts. Besides grain size, let's look in depth at two other characteristics of clastic sediments that give clues about how they were transported. First, when transported clasts have a chance to smash into each other many times in the wind or the water, corners of the clasts break off and they become more rounded. In landslides, the movement happens so quickly that clasts can't smash into each other for very long, so the clasts stay angular. While traveling in glacier ice, clasts are usually insulated from each other and spaced out in the ice, so they don't have much chance to smash into each other. The clasts stay angular too. In moving water or air, clasts do have many chances to smash into each other, so over time they become much more rounded as their corners break off. The other characteristic of clastic sediments that gives clues about how the clasts were transported is the sediment sorting. When wind or water currents separate out sediments of different sizes to move differently, sediments become better sorted and can become well sorted with pretty much just one size of particles represented. This happens in wave-transported sediment at the beach, in streams, and in the wind. Back to landslides and glaciers. In landslides, all the particles move together in a big avalanche down the hill so they don't get separated out by size. In glaciers, all the sediment's cushioned by the ice, so they don't get a chance to become separated out by size in that situation either. So if gravity or ice is doing the transporting, the clasts stay poorly sorted. Let's see what you're learning by trying these questions. Pause the video while you figure out the best answers and then play it again to see the answers. How did you do? A few more questions for you to try. Pause the video while you figure out the best answers, and then play it again to see the answers. How did you do with these ones? Alright, I've got a few more clues to help you separate out transport or environments that can give similar deposits. First, Both glaciers and moving water, like streams, can produce gravelly deposits. The differences between these two transport agents will be in the sorting and the rounding of the particles. Glacial deposits will have tiny to huge class, so generally be poorly sorted. Streams can have poorly sorted deposits too, but they're usually going to be a little bit better than glaciers. Notice the difference in shape though. This might be a big difference. Gravel from glaciers will always be angular, but gravel in other class transported by streams will be more rounded. Streams and wind can both give you sandy deposits or sandstone in the end, but wind's really good at sorting, so well-sorted sand is often from movement from the wind. Although it's oftentimes difficult to tell the difference in one single deposit from the beach or from just the wind blowing dunes around because they both can be pretty well sorted. So both well sorted sand, either of these environments is probably likely, and we're going to have to look for some other clues in nearby layers.